welcome to fifth and final Micromouse lecture. Yeah.
Of the few of you that are here, and I guess there will be a bunch of people watching online.
Yeah, hi everybody on the recording. That's probably like most people.
It's our fault for scheduling during small breaks midterm, but we couldn't change the time, unfortunately. So here we are. Anywho.
All right. So yeah, a lot of exciting stuff we're going to talk about today. Firstly, and just mainly overall, we're going to talk about maze solving algorithms, and in particular, we're going to focus on the Floodfill algorithm, which is what we're going to use for Micromouse. We're going to give a little demo on how the algorithm works, as well as so give you some tips on how to actually implement it on a microcontroller. And then also, we're going to go over some logistics for the rest of the year. I guess I should say before we get started, awesome job to everyone on their PCBs. We did order those. They're going to come soon. More on that later, but
yeah. Okay. All right. So now we can talk a little bit about some maze-solving algorithms here. Okay. So first of all, we have to talk a little bit about the maze itself. I know it's been a while since you guys have seen them, but this is kind of what the final mazes will look like. Of course, this is just a pictorial representation, but we'll have a big table that just has a 16 by 16 maze on it. Similar to what we did for the route competition, except big. So yeah, just to jog our memory a little bit. Remember that we're going to be starting in the bottom left, and we'll be going towards the goal, which is the center. It's going to be like a square, so 4 cells total, and entering any one of them is considered finishing. So as long as you get there eventually, you'll finish the map, the maze. So the point of our Micromouse is to navigate this maze with with literally no knowledge of what's of any of the walls. So all our rat knows is its starting location and its place where it's supposed to go, and that's it. So using that information, we can start and talk about a little bit of maze solving algorithms. So if you look here, here's a couple of super duper basic maze solving algorithms that aren't particularly smart. So here we can see that Dead Reckoning, I believe, just goes forward if it can and goes left if it can, and if it can't, then it goes right. And so, actually, I think it's the other way around. It turns right if it can, and I'm not entirely sure. I don't remember. Do you remember?
I mean, the algorithm works both ways. I don't know what this one is.
And then wall following just follows the left wall. So it'll just go forever and ever and never make its way to the center. So it's not very smart. So that's why we kind of need something smart like Floodfill. As we look at this, I think this will explain our some of the things that we look at for the maze solving. So of course we had the Dead Reckoning. That only works for paths and not branch mazes. So if we have things that branch off into different ways, it's not going to find its way back to the start. It's never going to go back or like take a different branch. Wall following won't work for things that where it has to turn right, where it can turn left. So we designed these Micromouse mazes so that approach just doesn't work, as you saw even in the last maze, it didn't work at all. And then the next one, you could just go randomly in any direction, right? That'll eventually get you where you want to go, right? It might just take absolutely forever and drain your batteries as you go with it. So that's not going to work. Here's Tremo's algorithm. This is kind of a interesting thing where you mark paths you visited and prefer unvisited ones. So this does get actually to where it gets to the center, but it won't always go to the shortest path, right? And then we have Floodfill. So this is the one that we're going to be using and talking a lot about, and it's going to guarantee our shortest path after we do a couple runs. In our case, we're only going to be doing one run, so most of the time your timing is going to be up to all of your PID constants, but Floodfill does guarantee the shortest path after it learns the maze well enough.
Just as a correction, in an actual Micromouse competition, you do get another run. You get a few runs based on what your mouse has learned on the. Basically, yeah. I guess the first round is like more about navigating the maze, and then you do have a round where you kind of go speed. So you do want to actually have the fastest route at that point.
Yep, my bad. Okay, anywho. Yeah, so those are the maze solving approaches and why we're going to use Floodfill. So here's kind of just the central idea behind Floodfill. And basically what it is just to find a path between our start and end point that's the most efficient. So what we do is, like, you think about pouring a bucket of water, like here in Minecraft. You can kind of look like the path that the water takes the shortest would just be around the side here, right? So that's kind of how Floodfill works. The water will flow around the walls and reach our starting point and our ending point, and it'll figure it all out. So let's see, yeah. Oops. Okay, yeah. So that's kind of how Floodfill works, like intuitively. Oh, I want to go back, please. And here, yeah. So the water just takes the shortest path between the 2 points, and our Floodfill, using our an algorithm as we learn the walls, we're going to basically figure that out. Yeah. So here's how it works technically from Dominic here.
Yeah, so we're going to talk about how, like, mouse is not water. How does Floodfill actually work? So the first thing that we need to talk about before that is the concept of a Manhattan distance. So your mouse cannot travel through walls. If you want to get from A to B, like, the shortest path is the Euclidean distance, which is just straight, but there's going to be walls in the way. So what we want is actually a Manhattan distance. And so that's going straight and go, like, I guess traveling on a grid, basically. The name Manhattan distance comes from the streets in New York, where, you know, it's very much laid out on the grid, and you need to drive your taxi from one place to another. So it's basically it's the number of cells in order to get to the goal, which is also the number of moves that your mouse needs to make in order to get to a certain cell. So basically our strategy in Floodfill is we want to move towards cells that have a smaller Manhattan distance to the goal. So what does this have to do with maze and mice? So this is how we can actually do Floodfill on our mouse. We want to assume that the maze has no walls to start. We have this goal in the center, and then basically outward 1 cell, 2 cell, 3 cells, 4 cells away, and we're going to start right here. So then once we start, we're going to try to travel as much as we can towards decreasing numbers, because that's going to give us, ideally, the shortest path to the center, still under the assumption that there's no walls. And so then if we get stuck in a point where there are walls, we're going to need to recalculate all of our Manhattan distances, because obviously what we have here, this isn't true. This isn't actually 4 cells away from the goal, but it is under the assumption that there's no walls. So as we learn about walls, we have to recalculate and actually find how far we are. So you can think of this back in the water example as it's kind of like re-pouring from the goal back to see then how far away our any individual cell is from the goal. So let's take a look at what this looks like. When we're traversing the maze, we're going to start here, and right at the start we can see that there is a wall right next to us. We go 1 up, we see another wall right next to us. We go up again, there's a wall up at the top. And now we finally go here and we hit a wall in front of us. So we've been following smaller and smaller numbers, which was great up until we hit this wall. And so now that's where we have a problem. We need to actually recalculate Floodfill now and update these numbers. Our mouse is stuck. So now this shows what the numbers were before, and then it shows what the numbers are after. Basically, any of those things that we've traversed, those are all going to get updated to be higher numbers because they are further away. So we have to go around this wall. Notice that, remember, there are other walls around here, but we still don't know about them yet, so we're just going to keep assuming that they're not there. So how do we actually do this, like in code? One thing that you'll need to know about is a data structure called a queue. So a queue is what's called a first in, first out data structure. We have basically a list of items. You can put things in and you can take things out, but you take things out of the end. And so we call that like adding an item to the back of the line is called in-queuing or pushing, and taking it from the front is called dequeuing or popping. And so we can basically use this as a list of cells to examine. If we have a cell, we could just add it to this list, and then we'll be examining these cells, adding new cells to the list, and then once we run out of cells, then we'll know we're done. So now that we know about what queues are, let's take a look at some pseudocode to explain Floodfill. We're just going to go through this, and then Tim is going to actually do a demo of this. So if you can't completely follow along, that's fine. It's going to be visualized a lot more soon. But basically, we're going to start by adding the current cell to the queue, and then while the queue is not empty, we take that front cell from the queue and basically take it out of line for consideration. And then we look at that cell, and then we look around at the neighbors that are accessible, not blocked by walls. And then if that cell is less than the minimum of its neighbors, then we need to reset that front cell to be the minimum +1, and then add those accessible neighbors to the queue. So this is kind of why it's called Floodfill, is that once we examine a cell, we're going to add a bunch of other things, like a bunch of the cells around it, to our queue, and you can imagine it kind of like floods out to examine all the cells. All right, and then once we're done with a particular cell, we're going to just continue, go back to the top, and then look at the other cells as described in this code. All right, so now Tim is going to show us how does this actually work.
Yes, I have to set it up real quick. Get this guy going. There we go. Okay, so here's just a little drawing of our flood fill here. This is the maze that we were just looking at, and kind of just a drawing out. So what I've done is I went ahead and labeled each of the cells so that we can kind of see which one's which. But as the first thing that we're going to do is go ahead and just do our Manhattan distance. So I'm just going to go through and label these cells. So we know that the center one is 0, and we're going to just go through, because remember, we don't know any of these walls yet. So all of these cells here are going to be 2, 2, 2, 2, 3. Okay. And now that I have set up our Manhattan distances, what we can do is start going like we did before, exactly how we envisioned, because right now we see that we can just kind of go ahead, no problem. So, okay. So we have our mouse here, and we see that we're on a 4, and we can go forward towards 3. Since that's a lower number, we're just going to go ahead towards 3 and towards 2, and then we're going to turn right and go to 1. Okay, so now that we're at 1 though, we see that, okay, so we want to go towards a number that's lower, right? And the problem is, okay, so we have 2's around us and a 0 in front of us, but there's a wall in front of us. Actually, let me mark this up here real quick. With the walls that we actually have seen thus far, we've seen these walls, and now this one. Okay, so with these walls, we're kind of stuck, right? So now this is where we come in and actually do flood fill. So let's just go ahead and do it. So what we're going to do is we're going to first add our current cell to the queue. As you can see, that's cell number L, or cell letter L. So I put it there at the bottom, front. So now we can go ahead and start. Since while our queue is not empty, we're going to take this cell out of the queue. We're going to look at it. And now we're going to get the minimum value of the cells around it. Okay, so what we can do is we kind of look at accessible neighbors, which means there's no wall in between them. So the only accessible neighbors that we have are G, K, and Q here. And we can see that they're all 2s. So the minimum number is 2, right? Now, what we know is our front cell number is 1, right? So L is 1. And that is less than 2. So what we're going to do is we're going to take our value, 1 here. We're going to go ahead and erase that and put a 3. Because that's 1 more than all of the neighbors around it, right? Okay. So now the next step, as you can see, is to add all of its neighbors to the queue. So it doesn't really matter which order you do it in. You can program it in whichever way you want. But I'm going to go counterclockwise. So we're going to do G, K, Q into our queue. G, K, and Q. All right. So now we just loop because we finished with our L here. So now we're going to go ahead, look at G, and put K and Q back to the front, right? So now that we're looking at G, let's see, G is this guy. Okay, so now we can look at its minimum value amongst its accessible neighbors. So let's look. Based on the walls that we know, which is the minimum number? Do you guys see the one? Around G. Yeah. So the minimum number here is 1, because we don't know that that wall exists. So since G is not, or right now 2 is not smaller than 1, we're not going to do anything with this, and we're just going to, let's see. Yeah, if the one's okay. Yep, then we're just not going to think about G anymore. Okay, cool. So now let's take K out, put Q here. Okay, so now that we're looking at K, we can see right here, we're going to look at the minimum of its neighbors. The minimum of its neighbors that we can see is 3, because we have L. We have L and P here. Both of those are 3. So since that's smaller, what we're just going to do is make this. Oh, my erase is too big. So we're going to make this 3 now, and add all accessible neighbors, which is going to add in P and L.
Maybe 4.
Did I make it? Did I write 3 again? Oh wait, hold on.
It should be 4, yeah.
Oh yeah, my bad. That should be 4. Okay.
Good catch.
The minimum. Thank you. Okay, and then we're just going to go ahead some more. We're going to look at Q here. So Q, the minimum number around it is 3. It's accessible, so it is less than that number. So we're going to make it 1 greater than those guys.
1, right? Because we don't know the wall.
Correct. You're catching me again. It is 1, so this actually stays 2. Good catch. You can tell how much I practiced this beforehand. Anywho, so we already did Q.
Luckily, your algorithm won't make mistakes like this.
Yes, if you program it right, it should be better than I am. So now we just have P and L left. Actually, yeah. So we have P and L left. So we look at P. P's minimum is 4, so we have to make this 5. And then remember, we also add the accessible neighbors to the queue, so we're going to add U here. And then there's P. Now we look at L. Oops. So now we look at L. L we already looked at. We're not going to do anything because we see that all the ones around it. Oh wait, no, sorry. Wait, what? Hold on. We take L out, and then minimum value amongst accessible neighbors is 2. And our value is not less than the minimum, so we're not going to do anything. Okay, and then, so we take out L. Then all we have left is U. And U, we see that 5 is the minimum, so we're going to make this 6. And remove that from the queue because there's no more accessible neighbors. Okay. Now if you look here, we've pretty much done a whole cycle, right? And now what we can do is go forward. Now that our queue is empty, we can go ahead and move our mouse some more. If I tap the right thing. So now we can go ahead and move right or left, depending on your program. It doesn't matter, because, or at least with here, it's not going to matter. Well, it will. One way will be faster than the other. But in general, it doesn't matter which way you go. So what we're going to do is go down to, oops. We're going to go down to 2. And then we're going to want to go to 1, and oh no, we're stuck again. What do you know? Okay. I'm going to do this one more time just so that we can, kind of see what's going on, and then we can go forward. I know it is a lot, like the first time, but hopefully this helps a little bit. So, again, we're here at, what letter is that? I can't see, it's Q. Okay, so we're at Q. Add Q to the list. Take Q out. And we see, okay, 2, the minimum ones around it. Oh, sorry. See a wall here. Okay. So now we know there's a wall. The minimum accessible neighbor is 3, so we're less than that, so we're going to make ourselves 4. And then we put in accessible neighbors, which would be L and B. And if you look at how this is going to shake out, okay, yeah, this should just take out L, and then the minimum of L accessible is 2. We're greater than that, so we're not going to do anything. And then, wait, that is correct, right? Yeah. Okay, and then after L, we're going to look at V here. I think this is, wait. I feel like I did something wrong with L. Okay, L. Get the front cell's minimum value amongst accessible neighbors. The minimum value is 2. Our front cell's value was greater than that, so we didn't do anything. That's correct. Okay. V, we have V here. 3, its minimum value is 2, so V is larger than that, so we're not going to do anything. So looks like that's all we did. We didn't edit anything else because we don't need to right now. But what we can do is now go ahead and move our mouse like here, and then we're going to pretend that this wall isn't here because I don't want to go for another 10 minutes on Floodfill here, so we're just gonna go there. Yay, we did it. There's no wall there. Okay, anywho, so that's kind of how Floodfill works. It is a lot, but it's relatively straightforward. And once you like do it a couple times manually, you'll probably get the hang of it. But that's how that works. So now that's it for the demo. Let's go back to what we're doing.
Alright, so that was our demo of how Floodfill works on paper, or rather iPad. But now we're going to actually talk about implementation. How do we actually implement this in C on our microcontroller? And if I can switch the slide, that is. Thank you, Tim. You may be wondering, how do we implement a queue? Queue is an abstract data structure, so there isn't really a built-in queue in the C language. We have to make it from other data structures. So there are 2 main ways that we can implement a queue. One is using a circular array, and the other one's using a linked list. The one we're going to talk about that's more straightforward is using a circular array. But both of these are considered valid. And so then that's our last point. As I was saying, C doesn't have a standard template library like the C++ language. If you're familiar from CS32, there is a queue data type that you can just use. Unfortunately, you don't have that available to you, so you actually have to make one yourself using either circular array or a linked list. So let's talk a little bit about what a circular array is and how does it work. So start is going to be like the index of the first item in the queue, and then end is the last item in the queue. So remember, for what queue only really has two things that we can do to it: adding an item to the back and taking an item from the front. So if we add an item, what we basically do is just add an item to the next element in the array that was not filled, and then we move our index, we increase it by 1, so that we know that like our size is 1 larger, so that we know basically which cells in our array have data in them. And then as for removing an item, it's also pretty straightforward. We can just basically move our start index. So we no longer care about what's in this cell. That is not part of our queue. We can just move one forward. This is the new start of our queue. And then, so why is it called a circular array? Well, an array normally is just like a line of data with like certain indices, 0, 1, 2, 3, 4, 5, 6, 7. But now we need to go back around. So you have to write some code basically that, okay, once we reach the end, our new index for the end is going to be back at the front. Now the whole thing is filled, so you have to keep track of that. So that's sort of just a general, some general advice on how to implement a queue using a circular array. Again, it's not the only way to implement a queue, but it's probably going to be the most straightforward. And so you may be wondering, okay, but like this has, like clearly it's like a queue, you want to have it be as long as you want, but this is a certain number of items. So, and that's basically, you need to choose a queue of a certain size of how many cells you're going to use. I think for Micromouse, 512 should be sufficient, but I kind of just made that up. You'd have to check that.
Yeah. Of course, it'll break if your start and end pointers end up at the same place. Then you'll have problems. So that's why you need a much larger, or a large enough array such that you'll never have that many things in the queue. So 512 is more than big enough.
Then just a few more tips that are going to help you with this assignment is that you'll need some sort of coordinate system to keep track of each cell and each wall. Where are we in the maze? So I'd recommend using a struct for that, which is in the C language. Basically, it's a group that has like different data values in it. So like it would have like an X and a Y and maybe a current Manhattan distance or something. And then you're going to want some arrays. You got to represent where do you have horizontal walls, where do you have vertical walls, and then what are your Manhattan distances for each cell. And then next, also when you're initializing everything initially, like remember when we had to go back, assuming that there's no walls, and then fill everything in, you definitely need to make sure you get that right. So yeah, you just have to, I think there be basically have there be no walls, and then basically assign everything so that under that assumption, and make sure you have those Manhattan distances loaded in before you start writing your code. All right, so I believe that is it for tips and I guess the technical portion of this lecture. Do any of you guys have questions about anything that we've talked about?
It's a little dense, but we'll have a lot more detail in the assignments. In fact, you guys will be writing everything for a simulator first, for a Floodfill simulator that we'll have. And essentially that will mean that you'll be developing the software, the Floodfill algorithm part, without having to have the mouse crash into walls and all sorts of stuff to see if it actually works. So your algorithm will be tested locally on a computer, and that will be through the next assignment. We're about to talk about that, so yeah. Yeah, any other questions? Yeah, what's up?
That cell L that was revisited in the algorithm.
Yeah.
Is that like redundant, or is there
We're looking at the iPad.
Oh yeah, this doesn't. I believe it was.
Oh yeah, when we had cell L happen
Yeah.
again.
Yeah.
I believe that's redundant. It might also end up having some things like if you have certain branch patterns, then having it go back there with new updated data might have some things change. Of course, that might be extremely specific to certain cases, but this is just how the algorithm itself works. I didn't design it, so I don't know the exact specifics or the reasoning behind why. But this is one of the most efficient ways to do this sort of pathfinding.
Yeah, and so it does like look at it again, but at least luckily it doesn't like just looks at the cell once. It doesn't like look through an entire path because that would be like time consuming. It just looks at like one extra cell. Yeah. Let's go back.
Okay, cool. So yeah, as I was talking about, assignment 6.1 is about Floodfill and using our little simulator. Let's see, yeah, so you're just going to be implementing it in C and testing it with our simulation and a bunch of different maze layouts. So that's all software, and you'll be installing it on your computer, and you could probably put it on GitHub if you wanted, work on it with your partners. So this is a more software-oriented portion of Micromouse. This will be due Wednesday, March 9th, which is in the middle of week 10. Did we finalize it?
This might be a lie.
Yeah, that might be a lie. Because that's like right before.
Well, let's do what Dav did. Let's survey the audience. What do you guys think? Assignment due in week 10 or assignment due like
week
during
2.
/ at the end of break?
Yeah.
During break.
During break. Okay.
Okay.
Then we'll probably do like week 0. Is there a week 0 of spring?
No.
Okay,
It'll be like week 1.
Okay,
Yeah.
there's like a week 1. So we'll have to do like the end of week 1 or something like that. So give you enough time to work on the software stuff. And then going forward, here's, I know you guys might have heard a little bit about it, but AMC, or All America Micromouse Competition, is going to happen sometime soon. So
Not too soon, don't worry.
Not too soon. We give you guys enough time to get Floodfill running and tune everything so that you guys will have a competition-ready mouse. But this is essentially where we're going to have our Micromouse competition, and there will be a bunch of other schools coming as well for various Micromouse programs from different IEEE branches. I hope that you guys win and crush them. We got a flex on them with our homemade PCBs and everything. So yeah, mark your calendars. That's going to be Memorial Day weekend, so more than a quarter away. But just know that that's coming up around the corner. Not really around the corner. The corner's kind of far away, but just know that you're going to want to be there. Okay, did I scroll too many times? Okay, there we go.
Yep. So then just some reminders of just stuff that's coming up. First thing is Officer Info Night. You see us up here, we're Micromouse leads. That has to be one of you next year, or 2 of you next year. So if you're interested in that, or if you're interested in any other officer positions at IEEE, there are a variety of admin and projects roles that are available. Come out to this and learn about it. We hope to see you there. It'll be great. Okay,
yeah. We talked about assignment 6.1 due. That's a lie. Due date. It's now end of week 1, as decided.
We have ordered the PCBs. They're coming. They should take like 1 or 2 weeks. So by the end of the quarter, week 10, they'll arrive, and also parts are coming in, trickling in. So hopefully at the end of the quarter, / definitely by the beginning of next quarter, you guys can get started on actually soldering and assembling everything.
Yeah, and then you'll have your own homemade rat to work on. That'll be a lot of fun. Yeah, okay. And then AMC, of course, the May 28th to 20th, Memorial Day weekend again. And I think that's it. Let's see, I think. Yeah, wait, is that the same thing?
Yeah, it is the same
That's the
thing.
same thing. Okay, that's the same thing as the first bullet point. But yeah, come to that if you're interested. We'd love to see you guys interested in becoming a lead for next year, if you want to do a better job than we did. Anywho, yeah, but that's it. So that's all we had for today. Thank you, the 5 of you guys, for coming out, and any of you guys watching online. If you have any questions, feel free to DM us on Discord or come visit us during the lab hours. Not a lot of you guys have been showing up. This quarter they're on Mondays, I believe.
Yeah, there's Mondays is like, I guess, I don't know if we have like official project lab hours but ours is basically Mondays from 3 to 6. We also, both of us have other lab hours too. Check website, come in the lab. There's also plenty of former Micromousers that can help out at other times too.
Yep.
So
feel free to ask anyone there, and they'll hopefully have a good answer for you. So yeah. Anywho, that's about it. Thank you guys for coming, and have a nice night.